we want to have these meetings can be completely public. We're going to record them, and ideally, we're going to go and write this up as an LWN article and submit it to have it be published when they do occur. So the idea is to, again, keep this open, friendly, and free, and do it like a birds of a feather. So hopefully everybody's seen the agenda document. If not, here, I'll go ahead and paste that in. Oh, thanks, Vincent. You got it. Awesome. Thanks. So we're more or less kind of keep to the agenda that's in here. Arnd, you are first up. So if you want to, I think you got some slides, so go ahead and take it away.
Thank you. So I'm going to talk about like the low end of embedded ARM and what that means for what we need to do in the kernel and what has changed. So the first question is, why now? Like, why do we suddenly have to care about low-end embedded on ARM64, and why didn't we have to care earlier? And what does it mean to be low-end? I'm going to go a little bit back in history. Like 10 years ago, we had embedded Linux on a large number of architectures still. The low end was kind of all the old stuff that ARM has been replacing. There was ARM v5 and then lots of MIPS, wireless routers. And then we were just starting to see 64-bit ARM displace some of the other architectures. 5 years ago, we had ARM64 already take over like the higher end tiers, anything that need a lot of CPUs, a lot of memory, or just performance at the time was starting to move to ARM64 from pretty much anything else. And x86 obviously is still around. And then ARM v7 was at the time the dominant thing on the low end, and it still is. So that's all 32-bit, where anything higher, anything that needs a lot of memory, if you have 256 megabytes of memory, yeah, chances are you already want 64-bit. And the way it looks now is ARM64 is making it into the lowest tier, the mass market of like camera chips, where you have a product that sells for under $20, where every penny counts, where you can't afford to have like a quarter gigabyte of RAM in there because it costs a few cents more. And suddenly we have 64-bit kernels on machines where we don't have that much memory. And previously we didn't have to optimize this at all. So yeah, this is what we're talking about. At the same time, something else is going on. This is the standard view of what a microkernel based machine looks like. You have different abstraction levels. You have device drivers that are completely isolated from a microkernel that doesn't do a lot. Well, actually, what people are doing is Linux is everywhere. So suddenly you have an Android system and you have virtual machines doing specific services that would otherwise be part of a monolithic kernel. And you have applications running in different virtual machines, even on embedded systems, not just in the cloud. And on these systems, if you have 5 or 10 virtual machines running on an embedded system, memory consumption starts to matter a lot more than it did if you only have one kernel running. So the question is, how small can we get a kernel, and how small can we get a system, and what can we do to make it smaller? The first thing when optimizing is always turning stuff off. And that starts very easy. You start, I did some experiments in the last few days. I started with the default configuration that currently gives us a 44 megabyte 64-bit kernel. And Mark Brown has already done some work on a simplified way of turning stuff off. So turning off all the SOC-specific code that we are not actually running on, that pretty much cuts it in half. And then it's not that hard to turn off a lot of other features. Everybody needs a different set of features, but few people need all the features. So I've just turned most of the stuff off that we have in the kernel. And within a few hours, I got the kernel, the image down to under 7 megabytes. And that still has a lot of features. The use case that I tried out was just booting a Debian virtual machine, being able to have network connectivity, still install packages, still use a normal file system, but have like graphics and sound and a lot of other things disabled when they use a lot of size in the kernel. So that makes it a lot smaller. Now actually running this, we run into the problem that user space is also big. I managed to run this kernel with 6.7 megabytes for the VM Linux in a virtual machine that has 40 megabytes, booting a standard Debian. I use DebVM to set up and run this machine with just a default set of applications installed. And I was pretty impressed. I didn't think we would get that small. I would think we would struggle at 100 megabytes, but 40 seemed doable. And then on the left side, you see how everything is used. So I added swap space, and the 16 megabytes of swap space are immediately used up. And then more than half of the actual RAM is used by the kernel. Some of it is the image, but most of it is actually stuff that the kernel allocates for itself, like page tables and inodes and everything that takes a lot of space. Then I tried running the same kernel using a 32-bit Debian install. So same set of packages, same user space, same functionality. Turns out we need only half as much for the kernel, and we only need half as much for user space. So that's much more comfortable. And for the rest of today, I'll assume that if you care about space, you'll be running a 32-bit user land. So we'll just throw away the 64-bit user land for now. 32-bit user space saves so much more memory than anything we could possibly do in the kernel. How does this compare to actually running a 32-bit kernel? That's also easy. I can build a kernel with the same configuration, 32-bit, and it seems like the kernel is also just half the size. So this is just for comparison. I need around 9 megabytes for a 32-bit kernel with the exact same configuration compared to 17 megabytes for running a 64-bit kernel. And the image size is about half as much than the initial allocations, and then anything that the kernel allocates at runtime is also half. And then the page cache, that is pretty much user space. So how does, where does this difference come from? Well, we have fundamental overhead, a lot of data structures in the kernel, anything, the executable code is pretty much twice as big for 64-bit. Every pointer is twice as big. Every instruction is on average twice as big. If you use 32-bit instructions and on 64-bit, but use thumb2 on the 32-bit kernel. And then there's some overhead that we have on both sides at the moment, but that we can actually, on 32-bit, we can make it even smaller, but on 64-bit, we cannot at the moment. And this is where I think we actually should do something about it. These are a few things that I just put out here that I think we should not be doing. So this was on some discussions on RISC-V where they made suggestions for how to make the kernel even smaller, and I don't think we actually want any of those, neither on RISC-V nor on ARM. But having a non-SMP config on ARM64 sounds like something we probably want. Like very few chips are actually shipped with a single core, but it does save between 1 and 3 megabytes of RAM on a 32-bit kernel. And you can buy chips with a single 64-bit core. Execute in place is interesting. If you have very limited RAM, but you have some executable ROM, you can put all the .text and .ro data into Flash, and that saves like 5 megabytes, which in this case is substantial. But it's also something that we have never done on ARM64, and it's rarely done on ARM32 as well. The main complication there is if you have the kernel execute from ROM, you can't do any runtime patching. But at the moment, we do a ton of runtime patching. We have CPU workarounds. We have the atomics that are used everywhere. So if you have an ARM v8.2 CPU, you want the modern atomics. But then if they're enabled, we also support the old atomics in order to be able to run on ARM v8.0. And this is something that I think we should change. The main problem here is that ever since we started ARM64, we have said we want to always support running on all the CPUs, including the old ones. So any feature that we add for new CPUs must be runtime detected. And I think the point has come where we need to reconsider this and make it possible to build a kernel that only ever runs on a more modern version of the instruction set, like a Cortex A55 that has LSE atomics. We can make the kernel smaller, and we can possibly enable execute in place if we do this. Then there was a patch for 32-bit ARM for eliminating unused code. I tried that out. It actually didn't make a huge difference, so there was just 90 kilobytes. I think there's more potential in there, and at least there's very few downsides. So this is just throwing away code that is guaranteed not to have any callers. So there's really no reason we shouldn't just throw that away. So this is something we can probably merge for both 32 and 64-bit. Going back to the SMP, there's some numbers that I did on 32-bit showing how, this does make a difference in my one test run. A few megabytes. There is all the spin locks go away, so the code gets smaller. And then we have the infrastructure for per CPU data. So even if you have just one CPU, but the kernel is built to run on at least 2, there's some overhead there that we can save. And that's should be easily doable. But it was a simplification on ARM64. We said no one was actually going to be interested in this. And I think this has changed. And then there's a few things that probably have a very small impact, but is something we could think about when we get the other ones done. And that's it.
All right. Thanks, Arnd. Anybody have any questions, comments, feedback?
Maybe one for me. Is it something that you're going to have a look at, the last feature you were mentioning, or is it just some idea that need more study? In your latest slide, there were 3 items.
Yep. I have done some work on the kernel stack, so the 12 kilobyte should be actually really trivial to do. That's something I might actually do. I don't think I would work on the 32-bit user addresses unless there's a huge interest in that. The compat mode is related to some work I'm doing on system calls. So if it depends how much interest we have from other people in making the kernel smaller. This would all be very easy to do if we really want to. The 32-bit user addressing is probably the hardest out of these. If anybody wants to ask a question but doesn't have a mic, there's also a link so you can type a question there and I'll see it.
And
Not
there is a
Arnd?
suggestion on the chat from Jonathan.
Ah, on the chat, yes.
It was a pretty random one, but things like execute in place might become interesting because we're starting to see, well, potentially anyway, the spec exists, the concept of read-only shared memory across multiple hosts, which brings an interesting idea for very big VM images and things, including the kernel, where you typically do copy on write on top, but nonetheless, a large chunk of it is effectively executing off the same memory across hundreds of hosts.
Yes, so execute in place, we actually have two completely separate things in the kernel that allow this. We have the DEX feature that used to be called ACPI and userspace, and that can definitely be used for across CXL to share like a file system across a large number of machines and have the memory only in one place. And this may be completely independent from sharing the kernel. So I was only talking about sharing the kernel. Sharing, like putting a file system on execute in place read-only memory is something that we can also do, which also saves memory. And I completely forgot about that in my slides. But yes, we can do both.
All right. Well, in the interest of time, let's keep things moving along. Jonathan, Cameron, you've got the floor next.
Yep. Can you give me sharing?
Yeah. So Arnd, if you want to.
There we go. Okay, so I kept sticking things on the agenda. So I'll cover a couple of them and then stop. And should it turn out that we have some time left at the end, which is inevitably not going to occur, I might cover some more. So we always have masses of things to talk about in venues like this, where we just want some sort of general inputs on them or raise awareness, all the usual sort of things. So I've tried to call out for the topics why I'm raising them. First challenge, can I change slide? Okay, I threw a quick list down of things we care about. Skip that. So this is actually a topic from Hanjun, Go Hanjun, who couldn't join us today because it's the middle of the night and he's got a cold. So he sensibly went to bed instead. So this is a current issue with memory error reporting, where the traditional solution is you get a nice ACPI event. It tells you got an error. You figure out where it is. If it's in a user space process, you kill it. Or right now you don't because it actually reports the wrong type of error. This patch set's been kicking around for really rather a long time. There is a fairly trivial question on the latest version, but this is, well, as you can see, it went to version 11. But it's definitely something we need to get cleaned up. And the solution is very straightforward. You basically make the task run the kill proc so that it's in the right context, everything reports correctly, and indeed the right process kills. So effectively, you tell it to kill itself. But I just wanted to highlight that one. This is a bigger topic. So this is something one of my colleagues in the UK has been working on. So the question I'm looking for here is, does anyone else care? We know some of the server vendors do. We've talked to a number of them, but I'm not really sure where else it applies. It kind of depends whether you have the controllable hardware and whether you care about the reliability control that this gives you. It's the classic trade-off between performance cost versus reliability. Yep, as it says, we're on version 6 of the RFC, so it hasn't got as far as a final proposal yet. Quick recap, what is memory scrub? Basically, you read memory back and you check the ECC. If it's got a correctable error, you correct it and report that you did. And if it's uncorrectable, you perform some form of asynchronous report. No, this isn't a CPU. Okay, one example it is, but normally it isn't a CPU doing this. It's autonomous in the memory controller, might be on the actual memory DIMM itself. So DDR5 brings ECS, which is, I don't know, can't remember what it stands for, but it means memory scrub out on the memory chips themselves. It can be in a memory controller as part of your SoC, or it can be out over CXL, etc. We need a solution for this because in CXL's case, we can't just punt it to firmware. Because firmware doesn't, they may well be hop into that path. So basically it's an OS problem. So stable connection isn't me disappearing. So the question then becomes, how general can we make it? Pretty said all that. There is some stuff in EDAC, but it's, well, it gives you a hint that it says SDRAM in the name of the function, which is not all that relevant to anything today. We could potentially extend this, but we don't always have a well-isolated thing that would have an EDAC device associated with it. These can be firmware controls across the whole system. So it doesn't map particularly well, but we could probably bludgeon it in if we had to. Actually, I don't really care. All I care about is getting the standard somewhere. The current proposal is a separate subsystem class, fairly standard ABI. There it is. So we've got, a name. We have regions because some of these controllers will support scanning with different settings for different ranges of physical addresses. Note the address here and size are all PA space. And then you've got enables and rates and this sort of stuff. I know DDR5 ECS is a pain. It's a pain because the specification is really specific. Rate control, it does very, very coarse controls over how it reports only. So it's not obvious how we can actually map that alongside the other things that exist, where it's typically in a memory controller. And the other open question on this is a feature of DDR5. Host controllers will receive this memory. Sorry, not this memory, this reporting. So far, I've seen absolutely nothing on what they do with it. Whether it's going to get reported up into the OS or whether people are just going to bury this somewhere in a BM error record. Happens to see. And that was the end of that topic. So probably a good point to hand over to someone else and then perhaps come back for more fun later.
All right. Thanks, Jonathan. Anybody have a comments, questions, feedback for Jonathan before we move on?
Lots of chat. That's me freezing.
Yeah, sorry.
Oh, that's okay.
At least you were
Did you
coming
hear
back.
me okay?
Yeah, I mean, we could hear you. I mean, and the good thing is you
that's
were
okay.
coming back, so it wasn't terrible.
Oh, okay.
But okay, why don't we go ahead and move on? Saravana, I believe you are next. Yes.
Yep, I'm here. Can you guys hear me?
Yes. Take it away.
Can I share? Okay, there we go. Oops, that's not what I'm trying to do. There. Okay. Kind of put this together in the last minute, so not fancy, a lot of slides. This is a bunch of to-dos I'm planning on working on. Just kind of shouting it out there in case people have any, hey, I would rather you work on something else related to firmware devlink or any related issues you might have. The first thing I'm planning on working on is, it's currently going on, I call it post-init-suppliers. Basically, if there are cyclic dependencies in device tree, firmware devlink has a information limitation on knowing how to break the cycle. So this property would allow us to kind of give that additional information to the firmware devlink or to any kernel for that matter. And once that's done, all the probing and suspend resuming will be 100% deterministic in terms of the sequencing. It'll allow us to kind of drive asynchronous probing and asynchronous suspend resume. Those are kind of the main reasons. I want to make suspend resume more stable. We're also going to improve runtime PM because firmware devlink allows tracking that. So that's one of the main reasons I'm kind of working on that. And then the other part is adding support for class devices to device link. So device link is kind of separate from firmware devlink. Firmware devlink uses it. It's a driver core feature where you can say, hey, these are my suppliers, order my suspend resume with respect to them. But you can also say stuff like, don't probe me until the supplier finishes probing. But the problem is class devices, they don't probe. You just add them. So the framework currently allows adding class devices as suppliers. So if you do that, you kind of get into weird behavior where your consumer will never probe and it should have. So I'm looking to fix that, and there are a lot of nuances to that. And when would you consider class devices as ready? When would you consider it as like not ready anymore? So you need to kind of unprobe your consumer. So that's something I'm planning to look at. And if these two don't take up all of my free time I have for the upstream work, then my third to do is to work on sync state support for the clock framework. We talked about this at LPC 2023 in a BOF, and different folks had brought up different gaps and all the different patches that have been sent out. We had some amount of agreement to try to clean up my patch series from, I think, more than a year ago. So I'm going to be trying to work on that to clean up or address the gaps Stephen Boyd had pointed out, and then send it out as a RFC or as an updated patch set to see how far that goes. And then one additional thing about the post-init-suppliers and the device link support. Bartos was talking about how if a supplier gets forcefully unbound for whatever reason, consumers don't necessarily get cleaned up correctly. They do get cleaned up correctly if the supplier is a bus device and it has a driver that can probe it. But if it's a class device, it doesn't work. Or if it's a bus device without a driver, it doesn't work. Some corner cases there that will also get fixed up as I work on these. So that's kind of my to this. Were people actually able to see my slides, or was
Yep.
okay, cool. That's all I have. Any questions?
So just for me, Saravana, so this should help the suspend resume time, I mean system suspend. That's what you're expecting for the first two bullets?
More like reliability, right? The reason
Okay.
we can't do asynchronous suspend resume today is because not all the dependencies are captured correctly. So we think we have captured it and we try async suspend, and suddenly a supplier suspends before the consumer and things break. Once we do that, then if we enable, we can definitely enable parallelized probing for sure with more confidence. Parallel suspend resume, I think there was a cost versus benefit discussion on is forking a thread cheaper or is it faster to just serially suspend some of the devices? So there might be some unknowns there. But this is more about we need to be stable first before we can optimize it. So this is taking the stable step first.
Okay. Okay.
And if you have any questions, my email is in this patch series I send out. So just kind of feel free to message me directly or an LKML.
Sounds good. Thanks, Saravana. Really appreciate it. Okay, Vincent, you're next.
Yes. Let me share maybe just one slide. There. So can you see this slide about system pressure?
Yep.
Yeah. So yeah, that's something I've started to work on few cycles before. So this has been presented at OSPM and LPC. So typically there is three parts: the green, the yellow, and the pink one. So the green one is merged and part of 6.8. It raised few regression, but normally everything is fixed. The yellow is under discussion on the mailing list with the new version, which have been sent earlier today, the V5. And then the next step from you will be the pink one, the arch scale CPU cap. So I'm going to work on that for the release after the coming one. And probably with having an RFC, and the main point there is to prevent when the user space is capping the frequency. We want to take that as a new maximum capacity in the scheduler instead of trying to do some kind of estimation of best effort and so on. The only things that I have right now it's about the naming of this interface, because we start to get a lot of large-scale CPU things. So I wonder if that's the best way to move forward on that. And I also see that there are some other patches going on in the mailing list, which would impact this as well. So yeah, that's really the last part that I'm going to work on. And if there is any advice about what would be the best name for that, I'm more than happy to get feedback on this. But yeah, I will probably work on that after the current merge window will be done. So that will be for the release after the 6.9. And that's pretty much, I mean, just to give an update on what was going. That will be the last remaining item for me. And with that, normally we should be able to get to take into account in a better way the user space capping in the scheduler and prevent any spurious wake up trying to migrate task when it's not doable at the end because of user space capping. And that's it for me. Do you have is there any question regarding that? Any concern or any interest?
All right. Sounds like silence.
Yeah.
All right. Thanks, Vincent. All righty. I guess we're back to Jonathan.
I should just have kept going. I've changed rooms, so with a bit of luck, I might actually have stable Wi-Fi. So, yeah, sorry, let me just the right screen. Oop, wrong page. Always a good start. Okay, so this is another topic that's kind of risen recently. And basically, I got this print message that you can see in the image on the left. So the problem we have here today is that ARM64 assumes that you know all about NUMA nodes at boot and that you don't need to know it after that. There are occasions, such as memory hot plug, CPU hot plug, in which you'd think, oh, I need to know the NUMA node, but actually the ACPI records always include it. They always include a number that tells you which one it is. So you don't need to keep it around. Recently, x86 added support for stashing it. So when they read SRAT, which is the big table of such things early in boot, they keep track of where all of the memory ranges that are defined are, so what the physical address ranges are, and which NUMA node they're in. The solution is horrendously Arch specific. It has sort of been adopted by Longsoon, but Longsoon just allocate entire chunks of their physical address range. So they basically divide it by, I think, 8 and declare that each 8th is a different NUMA node, and you just look it up on that way. So it's a very, very simple way of doing it, which is nice, but not really scalable. So the question around this is trying to generalize the x86 stuff is bad. It's pretty horrible. It's been discussed a number of times. A number of people have looked at it and run away in panic. And that's just because it's slightly too stitched in with how their early boot works, and it doesn't look anything like anyone else's does. So there was an option to move it over to memblock. It's never really happened. The real problem here, and the bit that everyone's really, really scared by, is trying to do dynamic NUMA node creation in Linux. There are a whole bunch of structures that are a real pain to allocate dynamically because we assume they're in a nice array and are dead easy to get hold of. So what everyone sort of thinks will end up there eventually, everyone's trying to punt that for a few years. It's an amusing conversation at every plumber's. It's like, who wants to work on this? And the answer is, well, no one. So why do we care? Why do we not have this information? So CXL memory, my favorite topic for finding weird corners of the kernel. In general, it's hot pluggable, but we actually know where it can be hot plugged. And the dirty hack and assumption that's there at the moment is each physical address range that you have is associated with a quality of service guarantee. And those could loosely be termed as suggesting where you might want to plug your memory. And in fact, there's a firmware query to say, where shall I plug this memory in? It has these performance characteristics, which physical address window shall I put it in? So the nasty assumption that's there is that for each of these windows, we declare a NUMA node. This is fine. It's read early in boot. There's a CDT table, which is, you read just after SRAT and you add extra NUMA nodes. Unfortunately, the problem is we don't keep them. So we create the right number of NUMA nodes, but we don't know which is which because we don't have any record. So the question then becomes what to do when we do get hot plug of memory. So option one is stash the results. So copy something similar to x86 or indeed implement our own version, which would be horrible. Another option, which I kind of like, but is very hacky, and I'm wondering people's views on whether it's too hacky, is we can just pass the ACPI table again. We know where the NUMA nodes used by this table start, and we know them in order. So we can just work our way down through the table and go 1, 2, oh, it's number 3, and put it in there. And so that was the possible quick solution to this problem. Before I go any further, am I actually stable this time? Good. I saw Tom nod. That's better. Don't know what it is about that other room. Okay, so that was one of the topics we've raised. We'll be looking at this next kernel cycle because we need this fixed. We run into a whole bunch of issues in QEMU around TCG and page tables and stuff recently. And the only way to get them to actually occur on ARM, they occurred really easily on x86, was to bodge those functions that I showed on the previous slide to always return the answer number 1 rather than no NUMA node, which is what they do today. So it was an easy bodge. Okay, one last topic. So this is one I've run into a few times recently. Again, yeah, Compute Express Link, more problems. So the fun thing about CXL is it has kernel features, which are typically around presenting things to user space interfaces. Some of them, so normally you think, okay, we've got a user space interface. The worst that can happen if I get things horribly wrong is I can take myself out. You've got root permission on a server or whatever, you can probably crash the kernel if you're determined enough. You can certainly make it do evil things. Now, the fun bit on the CXL interfaces is you can take out the rest of the rack or potentially the rest of a data center because you can reconfigure switches that are going to memory and you can remove everyone else's memory. And yeah, you think, well, there'll be security measures on this. And yeah, there will. The problem with some of these interfaces is they're in band. So they're sat there on PCI devices. And the idea is that you lock down that port and you only connect that to a BMC and the normal host can't talk to that particular port that has the magic interface. Now, the pushback we've had on this is that some of the kernel folk are very, very scared of getting a security bug that means you can take down a rack. So they're very scared of introducing these features at all to the kernel, despite the fact that they should never be wired to a machine that would have, should we say, loose enough security guarantees. They're typically only wired to a BMC or a fabric manager, which is basically a specialized BMC running special firmware, lots and lots of rules around it, lots of crypto, all of the usual stuff to prevent people poking the wrong switch. So the question here is, it actually applies as well to the whole MCTP stack in Linux, because once you're out on an MCTP network, you can do all sorts of horrible things. And there are host controllers. This is another thing to take into account, is that these are not BMC only. There are server chips out there that have MCTP controllers, for instance, as well as the inbound interfaces. And you really, really don't want to turn them on. They will have a normal kernel driver. They'll have, in the case of MCTP, a nice network socket on which you can sit and chat away to whatever's on the other side of the connection. That can be, yeah, pretty nasty. So the basic problem here is some of the kernel guys, including some of the CXL maintainers, don't trust distributions. We don't trust them not just to turn on the new fancy feature. Sticking big warnings about, yeah, if not sure, please disable this, generally doesn't work. They get turned on anyway. I've seen all sorts of fun debug features turn up in distro kernels. So the question then becomes, what do we do about it? How do we prevent people shooting themselves in the foot? One option we have been kicking around, and this is why I'm looking for feedback, is a config BMC. Bury it somewhere and basically have, hopefully, anyone configuring a distro knows what a BMC is and goes, am I a BMC? No, I'm not. And doesn't turn it on. And then you gate all of these features behind it. So it's a bit like some of the expert controls or tiny ones we've had in the past for particular system classes, where you're trying to stop things getting configured that make no sense for a normal machine. Any other options that anyone would like to suggest would be welcome as well.
Isn't there a possibility to shortlist configs that are deemed non-secure? I mean, somehow that's what you're asking for, well, for distros not to pick them up.
It's an interesting question. Is there a path to tell distros to genuinely don't pick this up? Don't turn this feature on. I mean, in theory, there's lots of notes in the kernel kconfig that say basically enable this at your own risk. Any of the error injection stuff is in that category. But it gets turned on anyway.
But there is no such class per se. I'm asking question actually.
Mm-hmm.
I mean, no, there isn't. I mean, config BMC is just a naming, right? I mean, it's
Yeah.
It's
put something like that. Config I am a BNC maybe, or config something. So the question is whether a top level, well, fairly high level config option would be the way to prevent this, and then to add that list, because you just make everything depend on it that you don't want to be available on a normal machine. I mean, these interfaces are really handy for testing, so I'd have them on anyway, but I don't want them to ship to anyone.
Yeah, so maybe we actually need something that we have on ARM32 and on RISC-V now, which is an option that says, am I a generic kernel that can run all kinds of machines, or am I a deeply embedded kernel? And this could be behind the non-generic option, so that in a distro, you would never be able to turn it on because the distros by definition want the generic options. And the same thing would be for execute and play. So anything that breaks running on some other machine.
The
Yeah, okay.
topology I was thinking about was, okay, CXL matures a bit. We're a few years down the road, and now I'm creating sort of a high performance embedded system with 2 nodes connected with CXL. It's only myself that I can damage. I don't have a BMC. Maybe I want to turn these things on.
These don't do you anything. They don't do anything useful for you. If you're in a system that's that small,
Yep.
These are typically things like reconfigure the routing on a switch. It just doesn't do anything helpful.
So you would think on a system like that, the firmware would set all that up and the kernel would never touch it.
I think it would be baked in. If there's a switch there, it's loading it from a flash or something. You wouldn't bother. This thing requires typically big, expensive wiring.
Okay.
So they don't occur on simple systems. So the smallest system you see this on is something connected to a multi-head device. But it has to be a configurable one where you can move memory around between different hosts. Would be the sort of minimum. And you could see that happening in embedded, but the question is who would control it? And this is one of the reasons the spec has this interface, is precisely that you might have a small enough embedded system that you do want one of your hosts to also act as the control node. So we do kind of need a way to turn it on. And we don't want to make it too bad, because we want to turn it on for testing, because we use all of these interfaces to poke QEMU models and things to make things move around.
And really, I'm just debating the name. And so if but if there's a lot of other BMC specific assumptions that get baked into this config, that's what I would worry about.
Yeah, that's fair enough. Yeah, the name's a bad one.
So
yes.
If we want to discourage people, we could taint the kernel. I've thought about different dangerous options in the past, and like maybe we should taint the kernel in that case. Maybe here it's not appropriate, but an idea for discouraging people.
Stop sharing. Sorry. Brought my notepad up. Yeah, I mean, we already taint for a few things in CXL. So we taint if we don't have access to a global cache flush, which we don't on ARM. So it's certainly a model we're already doing for some of the nastier corners but they're usually things with correctness problems, where you're testing. It's fine to do it as long as you're very careful, and just occasionally it'll blow up on you. But I guess we could add a new type of taint, which should put people off sufficiently. It's definitely an option. I guess maybe this is a question of float a patch set with one of the options and see what replies we get. To be honest, I just don't want to carry on carrying lots of code out of tree. So got to get it in somehow. Anyhow, that's all I had. So thanks for the feedback.
I didn't get the previous problem, what it was, Jonathan, related to the SRAT. So if you can just summarize it quickly.
So SRAT defines all of the NUMA nodes in the system, with the exception of CXL fixed memory windows. Now, SRAT, the advantage. So SRAT is very useful for telling you where things are at boot. After that, we throw all of the data that's gathered from it away. We don't keep track of the physical address ranges, etc. We could read them from SRAT again, but at the moment we don't. So they're kind of done. If there's no memory in them at the time, or the SRAT node's empty, we don't store any information about it. Then if we do memory hot plug later, the ACPI hot plug event includes the memory node, includes the NUMA node. So we go, it's that one. And the same is true of CPU hot plug. So in both those cases, we have the actual record that's telling us that memory's been added, includes the missing data. For the CXL fixed memory windows, as I say, there's a hack at the moment that means we end up with a load of extra NUMA nodes. The problem is we don't know which is which. So the question is we have to re-establish that, because the fact you've plugged a CXL device in, it's all in the realm of the OS. It's not in firmware. So the firmware can't inject its idea of which NUMA node that is. We have to establish it somehow, and we can do that by just rereading the ACPI tables to basically work out what the flow was that happened earlier. So we can now work out what number to use now. Or we can go and add a whole bunch of infrastructure. And I think the problem is that if we start adding the infrastructure, we'll get strong requests that it needs to be cross-architecture, and that code is evil and inconsistent across the different architectures.
It's
So
evil because it doesn't rely on firmware information, it relies on probe ordering or something.
No, they all rely on firmware information. The problem is in x86 world, there's a whole bunch of extra firmware tables that are not SRAT that get all looped into the same code paths. They then generate a bunch of NUMA and meminfo stuff that they just stash in a big array that sat there loaded as part of kernel text. So you can do it. It's just a much bigger job than the, shall we say, dirty hack of just rereading the table. So the question is, from a philosophical point of view, is rereading the table fine? And it's a bit unusual for an ACPI table to read it at random runtime sometime later. If it is, it's a lot simpler.
I mean, I suppose, well, of course, it's a static table. I don't see why, I mean, I don't get why it's a problem to read it again, actually.
Okay, I mean, that was definitely an option. It felt out of the philosophy of how all the others are handled. So it's a bit of an unusual from that point of view. But yeah, sure. I'll start with that approach and then see what reviews we get then. That's a quick hack. So that's 2 days work rather more for the other one.
All righty. Well, I think we reached the end of our agenda. Thanks, everybody. Thanks for your participation. Thanks to all the presenters. And we'll do this again in advance of the next kernel merge window when that opens up. So have a good one. Cheers.
Thanks, everyone.
Bye.
Cheers.